So in the last lecture, we started with understanding inductive effect, right? So to understand inductive effect, we took the example of alkyl halide. In the alkyl halide, as halogen being more electronegative, you have partial negative charge on it, and you have partial positive charge on this carbon. As this carbon has now become deficient of electrons, it tries to pull electrons from the adjacent carbon. Whenever it is pulling electrons from the adjacent carbon, it may not pull to the same extent. Hence, you are having a relatively less negative charge induced on it because of this particular sigma bond. So we have delta delta here. We also saw that this delta is much significant when compared to delta delta. So overall charge on this becomes only partial positive. On this it becomes partial delta delta. On this it becomes partial triple delta. And this itself being very small, after the third carbon in general we won't take any inductive effect. And whenever you have inductive effect, we can define two types of groups. One which pulls electrons towards itself, one which donates electrons, or one which pushes electrons in the sigma bond. So whichever pulls electrons or whichever withdraws electrons will be called as minus I group. Whichever pushes electrons will be called as plus I group. So all plus I groups after the inductive effect will be having positive charge induced on them, and all minus I groups will be having negative charge induced on them. And I asked you to add more things. Here you can add a few more things. Like you may add CH2 minus, will be having even more inductive effect when compared to O minus, and NH minus will have even more inductive effect when compared to O minus. You can add these things, but this is sufficient. This order is sufficient, and I have added few things in this particular group, and we also corrected some things, right? I will check the correctness of OH or OR, whichever is greater. But C6H5, in most of the orders, it was given C6H5 to be lesser when compared to the alkyne. Alkyne is given greater. So let's stick to that order. We will see. Okay. Then applications, in the applications of inductive effect, or in this chapter, we will be comparing lot of acidic strengths and basic strength order.
Sir,
Whenever you are having an, yes.
sir, that C6H5, the order changes now, sir, compared to what you gave originally.
Yes, yes. The
Yes,
order,
sir.
the order
Sir,
is changed. That's what I'm saying.
question. We did a
Yeah, the
question.
question. The question also changes. So today, after the class, I will check the pKa values. So once you check the Ka values of those compounds, if at all it is available in literature, we can get an idea of whichever is having greater minus I.
Okay,
Okay.
sir.
So I'll check the Ka values. Accordingly, we will have justification of whichever is having greater minus I. Yeah. Whenever you are comparing acidic strength or basic strength, an acid is one which gives H positive. So if it is giving H positive, it converts into negatively charged species. So you need to look for the stability of the conjugate base so that you can analyze how much H positive is present in the system. So if more and more H positive is there in the system, that means A minus is relatively stable or it is not combining back with H positive. So this being negatively charged, we need to look for those entities inside this which is stabilizing that negative charge. Negative charge can be stabilized whenever you are trying to pull that negative charge, right? So electron withdrawing groups is going to increase the stability of the conjugate base, and electron releasing groups is going to decrease the stability of the conjugate base. So electron withdrawing groups increases the acidic strength, hence minus I groups increases acidic strength. A base is one which donates its lone pair to H positive, and overall conjugate acid will be having positive charge. So this being positively charged, if I want to absorb or accept more and more H positive, this positively charged species must be stabilized. So positive charge can be stabilized whenever you have electron releasing group, right? So electron releasing groups will increase the basic strength, but they will decrease the acidic strength, right? Okay. So after that, we did some questions, and then I think we moved on to resonance. In the resonance, we started with understanding why resonance takes place. Resonance is going to happen in order to attain stability. And how exactly the stability is attained? Because of delocalization of the electrons or delocalization of the charge. If the charge is localized or concentrated on one particular atom, it may not be able to effectively stabilize it. If the same charge is distributed on several atoms, it can stabilize it effectively, right? Like in the case of O3, you have negative charge either concentrated on oxygen 3 or on oxygen 1. Whenever you are forming the resonance hybrid, the negative charge got distributed equally on both of these oxygens. Hence, this system is considered to be more stable when compared to either of these two systems. Also, the pi bond also got delocalized. Initially, it is concentrated between 1 and 2 or 2 and 3. Now, the electron density is distributed among these three oxygens. Agreed? So, whenever there is delocalization of charge, there is going to be attainment of stability. So, resonance is happening in order to have stability inside the system. Next, we started with understanding when can this particular resonance happen. Because whenever you see negative charge, you may not distribute that randomly on different atoms. There are certain rules or there are certain cases where that negative charge of the pi bond can be distributed. You cannot randomly distribute that on the molecule. Agreed? So we are trying to look when there is possibility for the distribution of that negative charge through resonance. And the other important point in resonance is taking place through the pi bonds, and through the pi bonds, electrons are being transferred from one atom to another atom significantly. And pi bond being a weaker bond, there is effective delocalization of the charge. Hence, resonance is considered to be much stronger effect when compared to inductive effect. If you want me to compare inductive effect and resonance, if I give a score 1 to inductive effect, the score for resonance will be 1 million. Okay, that is 10 lakhs. So it is 1 million times more stronger when compared to inductive effect. So in the presence of resonance, inductive effect is not that significant. Is not that significant, but wherever you have purely inductive effect, we may have to know the order of the inductive effect of different groups. Is that clear?
Yes, sir.
Okay. Okay. So let us try to understand when can this resonance happen. I think we started answering that. So resonance occurs in conjugated systems. So whenever you have a conjugated system, there will always be resonance. So we need to understand what's meant by a conjugated system. Conjugated systems are those systems where you have symmetric p orbitals present on three or more adjacent atoms. As an example, I have taken 1, 3 butadiene. So if you take 1, 3 butadiene, this is the structure we may write. This is the Lewis structure we may draw. But the actual structure of 1, butadiene is this. You have carbon, 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 and there is electron density present between any of the two carbons. The pi electron density is present between any of the two carbons. The amount of electron density may differ. That is, the amount of electron density that is present between these two carbons may not be same as compared to electron density, the pi electron density present between these two carbons. So we need to understand how or what factors that are going to determine the distribution of this electron density. Okay. So first of all, let us understand, is this a conjugated system or not? So for that, you need to know hybridization and you need to know how to do the analysis of pure orbitals, all those things. So if this is sp2, whenever you see one pi bond on the carbon, you blindly mark it as sp2. So this is sp2, 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 sp2. So if I take spx, py participating, you are left with pz. So if it is forming pi bond is always formed between symmetric orbitals in order to have sidewise overlap. So this has to be pz. And if this is in xy plane, the these hybrid orbitals must also be present in xy plane. Then only you can have that head-on overlap. Agreed? Okay.
Agreed.
So you have this also spx, py. So you have pz orbital, you have pz orbital. So you have parallel symmetric p orbitals present on three or more adjacent atoms. So this is a system where resonance can happen. So let us understand how that resonance is happening, or let us try to draw some contributing structures which will help us in making the overall resonance hybrid. Okay. What is the maximum capacity of any orbital?
Two. Two
Two
electrons.
Two
electrons.
electrons.
2 electrons, right? So if you have 1 electron here, 1 electron here, 1 electron here, 1 electron here, initially there is pi bond between these two and pi bond between these two, right?
Yes, sir.
We are only seeing the way to form different resonating structures. Okay. We are only trying to identify all possible resonating structures which can lead to, or whose different contributions can lead to the overall resonance hybrid. Okay. So what I'm going to do is, as any orbital can have maximum of 2 electrons, I'm going to shift this electron completely into this. Is that possible? Because this orbital can have maximum of 2 electrons. Whenever I shift the electron completely into this, I can mark something like, you have an electron here, you have an electron here. Now you have 2 electrons here. This particular orbital has no electrons. So I can say this carbon is going to have a positive charge now because this has lost its electron to this carbon. Agreed? As this carbon is gaining an extra electron, this is going to have negative charge. So the initial structure is of this. The initial orbital diagram is of this. This I can represent it as, you have a positive charge here and you have a negative charge here. Agreed? Similarly, what I can do is, I can take this electron into this orbital. If I take that electron into that orbital, I can show 2 electrons in this, 2 electrons in this. There are no electrons here, so which can be shown as positive charge. There are no electrons here, which can be shown as positive charge. This is gaining an extra electron, so there is a negative charge here, there is a negative charge here. So its structure is going to be, have positive. On this carbon, you have negative. You have positive again. And on this carbon, you have negative. Agreed? Or the way to show it is, what I'm doing, I'm breaking the pi bond. In yesterday's lecture, we saw rules for writing the resonating structures, right? So a pi bond always breaks and converts into a negative charge. And a pair of electrons or negative charge always forms the pi bond. Remember? So what we can do is, you break this pi bond and you convert that into negative charge onto this. So which is nothing but this structure. Agreed? Similarly, what I'm doing here, I'm breaking this pi bond, I'm taking this onto this. So which will give me negative here, positive here. Equivalent orbital diagram is this. Right? Next, what can I do? You can, everyone, you can take the electron and shift into this orbital. Once you do that, what will you have? You have an electron here, you have an electron here, you have 2 electrons here. Once you have 2 electrons side by side, you can form a pi bond between these two, right? So I will show that as C double bond, sorry, C, you have positive charge here. Now this carbon won't be having any charge. You formed a pi bond between those two, and this has a negative charge. Agreed? So what I'm doing here, wherever you see positive and negative side by side, you can always form a bond between those two. So I have formed a pi bond between these two, and I got this. Understood? Okay. Then again, what can I do? Again, you can take this into here. Okay, as this has already formed pi bond, you can take this into here. You can do several variations of it, or you can directly mark a structure. Take this negative charge and form a pi bond. Carbon cannot make 5 bonds, right? So what we will do, you break the pi bond and take this as a negative charge on this, which will give me this structure. C positive bond, C. You have a negative charge here. Then you have double bond C. You are seeing negative and positive side by side, form a bond, pi bond. So you got back the original structure. Understood? Okay. So these are resonating structures or the contributing structures which will help us in making the resonance hybrid. Okay. So this particular resonance hybrid, whatever has formed, it has formed by overlap of all these orbitals. Can I say that? You have parallel electron densities. What we are doing is at the end, you are drawing something like this. Let us try to show something big. So you are having overlap here, overlap here, overlap here, overlap is happening here. So all these parallel p orbitals are having overlap among each other, and you are having the pi electron density distributed from here to here. The extent of overlap may differ. Okay, the overlap of this and overlap of this may differ. If this is having stronger overlap or more overlap or greater overlap, the electron density here will be greater. Okay, so how to judge that? That is just based on the stability of these resonating structures. Okay, so whatever resonating structures, whatever possible resonating structures you are making, they are going to contribute to the resonance hybrid in different percentages. If all the resonating structures are of the same energy, they are going to contribute to the same percentage. In case of ozone, you have two similar resonating structures, right? Or two equivalent resonating structures. So their contribution is 50-50%. Hence, you are able to form the hybrid by simply doing the average 1 plus 2 divided by 2, right? In case of carbonate, you had three resonating structures. All of them are the same. So all of their contribution will be the same. So 33.33, 33.33, 33.33, or sum of all those things divided by 3. Yeah, Rajesh.
Sir, if which one has more electron density depends on the stability of it, then how will buta 1, 3 diene and buta 1, 2 diene be different?
In 1, 2 diene, you won't be having resonance. They are not present in parallel orbitals. That's the case of cumulene, right? They're not present in parallel orbitals. Once you try to draw the pi
Okay,
bond,
sir.
px and py will be overlapping, right?
Yes, sir.
So there
Okay,
won't be any
sir.
resonance there.
Okay, sir. Sorry, sir. Got
Okay.
it.
Yeah, everyone. So what we want is we need to know, first of all, you need to try and draw all possible resonating structures. Whenever you are drawing resonating structures, you can form multiple resonating structures. Some of them may be highly unstable, so they may not be contributing to the resonance hybrid at all. They may be a valid structure. It can be a valid structure, like, let us say, you are making something like this. Suppose you have C double bond C bond C double bond C. What I'm doing is I'm breaking this pi bond here and I'm breaking this pi bond here. Okay, which will lead to formation of this structure. You have negative charge here, positive, positive. This can be a valid structure because you have a completely vacant orbital, two electrons here, completely vacant orbital. But this doesn't contribute to stability of the overall resonance hybrid, or in a way, I shouldn't be forming this structure only. But if they ask if this is a valid resonating structure, yes, it is a valid resonating structure. It is a valid structure. Okay, but two negative charges on side atoms or on adjacent atoms is highly unstable because of the repulsive forces. We are doing resonance in order to explain the stability of the molecule, right? So why will we take unstable resonating structures and try to explain the stability of the molecule? So the conclusion is you may draw some valid resonating structures without them actually contributing to the resonance hybrid. Suppose this particular structure, if you see, this structure has lot of charges. Whenever you have lot of charges in the system, all those structures are unnecessary. Okay, that contribution of it is almost equal to 0. So in this case, even this is considered as one of the resonating structure because it is not the actual structure, right? if I see all these structures, whatever structures I have drawn here, this is a neutral structure. This has some charges, but the charges are less when compared to this. So if I want to check the contribution, I can say this will be contributing to the highest, followed by this and these structures. Okay, we will see the rules to identify the stability or the contribution of different structures soon. As of now, some idea, this is having two charges or it is having this carbon as octet incomplete, right? So this is going to be less stable when compared to this structure where all the carbons octet is complete.
Sir, in the
Agreed?
fourth
Everyone?
carbon, yes, sir, in the fourth structure, yes, sir. In
This
that
one?
structure, does it
Yes.
contribute more than the second structure because the charges are very distant to each other, despite their neutral?
We will look into that. We will look into all those things later. But as of now, this will contribute more. Reason being positive and negative. Unlike charges, if they are close to each other, there will be more attractive forces, right? When compared to far from each other.
Okay, sir, yes.
Okay. We will do those things. We will go step by step. So as of now, just understand only this thing, everyone. If I have this structure, you need not show orbital diagrams for everything. Initial few examples, I will be drawing orbital diagrams and show how electrons are getting or how to frame those resonating structures. Later on, we will also try to see some molecular orbital aspects of it. Okay, but you need not draw these things all the time. You just need to understand how to shift the electrons from one atom to another atom. Whenever you have a pi bond, you break that pi bond onto the atom. Whenever the pi bond breaks onto the atom, it converts into negative charge, which is two electrons. One electron of this carbon itself, and the other electron is coming from this. So you have two electrons. Fine. So you have negative charge. Any negative charge is always represented by two electrons. So I am showing two electrons here. This is having positive charge. In the next case, what I did, I have taken this pi bond onto this and negative and positive. Too many charges. This structure has too many charges and therefore will be an insignificant contributor, or it is highly unstable. So shouldn't be drawn. Shouldn't be drawn, or you need not draw it to frame the resonance hybrid. Okay. Then see the other structures, negative and positive side by side. I'm forming a pi bond. Then what I'm doing, I'm converting this negative charge as a pi bond. As carbon cannot make 5 bonds, I'm breaking this pi bond and I'm taking this onto this as a negative charge. Next, negative and positive side by side, again pi bond. In the initial structures, what I did is I have broken this pi bond onto this carbon. We can also do the other way. I can break this pi bond onto this, right? So I'm doing the other opposite way, breaking this onto this. So this will have negative positive. Then I'm shifting this onto this. I am omitting the high charges structure. So directly I'm forming, once you form this, you have negative positive side by side. I'm directly forming a pi bond. I directly jumped from here to here, everyone. I have not formed the structure which is having greater number of charges as it is unnecessary. Everyone with me?
Yes, sir.
Okay, then this structure. So if you observe, there can be others possible other structures as well which are unnecessary. So I have not drawn any of those structures. So these are some valid structures. In general, there is a question that is usually asked, the number of resonating structures of a molecule. So whenever they ask that, they're asking for the more contributing or more stable structures. Because the number of resonating structures, you can draw many resonating structures. They should be valid, that's it. If they are valid, you can draw it, but they won't be contributing to the resonance hybrid. So whenever such a question arises, you always go for more stable or more contributing resonating structures. Fine. Okay. Once observe this, I'm saying this is the major contributor. And as this is having, if you observe, apart from this, rest all other structures are octet incomplete. Right? Because this has positive charge, carbon with a positive charge, carbon's outermost electrons are 4. Positive indicates you have removed an electron, so you have 3 electrons. You have formed 3 bonds, one with this, and one with hydrogen. So 3 into 2, 6 electrons, right? 6 electrons is octet incomplete. So whenever carbon bears a positive charge, it's always octet incomplete. You can blindly say that. You need not check. Okay. Carbon bearing a negative charge, it's always octet complete. Because carbon's outermost electrons, how many? 4. Negative indicates you have given one more electron, 5. Out of those 5, 3 bonds are formed. So 3 into 2, 6 plus 2 electrons are left, which is a lone pair. So you have 8 electrons. So carbon, whenever it has negative charge, you need not check if it is octet complete or incomplete. It's obviously be octet complete. Carbanion is always octet complete. Carbocation is always octet incomplete. Fine. So this is an octet incomplete structure. More octet incomplete because 2 carbons are incomplete. Octet incomplete structure, octet incomplete structure, octet incomplete structure, octet incomplete structure. So out of all the structures which I drew here, this is the major contributor. Okay. I need not have any contribution of this structure. You can simply omit it. And next, what
But I
are we
have a
having?
doubt, sir.
Yes.
Sir,
Go
in the
ahead.
second question diagram, that minus charge, and you have written 2 dots on the top, no, sir?
Yes.
The 2 dots on the top represents the minus charge, no, sir? It's not individual.
Represents the minus charge together. One electron of the carbon itself and the other electron coming from the other carbon. Hence,
Okay,
negative. Okay. Whenever you have negative, it can always be shown with 2 electrons on it.
understood.
Okay. Okay. Everyone. So whenever I'm taking the contribution, this structure is the major contributor. Next, if I'm taking contribution of these, once observe, this structure, where is the other structure? Okay, this structure you have, did I mark that? Maybe I have not marked the exhaustive list. I wanted to show some structure similar to this, but with the negative and positive here. You have negative and positive here, right? Okay. So similar structure can be drawn. Like if I am taking this pi bond on here, you have negative and positive here. So the contribution of that, or else let us take these two structures, everyone. Let us take this structure with this structure. More or less, they are looking equivalent, right? More or less. Or else, let's forget about this also. Let's mark 4 and 8. Can I say both of them are exactly equivalent?
Yes, sir.
You have positive negative pi bond, right? So can I say their contribution will be exactly same? If their contribution is exactly same, can I say this positive negative cancels, this negative positive cancels? And because of the pi bond appearing here, you will have some pi bond character overall in the resonance hybrid. Agreed? Because I'm taking some percentages of this in calculating resonance hybrid, right? So there has to be some pi bond appearing in the resonance hybrid. Agreed? And
Yes,
you
sir.
take this structure and this structure, everyone. You take this structure and this structure. You have negative, positive, positive, negative. More or less, their contribution to hybrid is less, if at all they're contributing. Also, even though here I'm saying, see why I'm saying they won't be contributing to the same percentages. They're not equivalent. Okay, try to
That
understand
is
this.
because of that double bond, C bond, that there's a I minus group and it's
Yes,
stabilizing the
here
electron.
negative charge is adjacent to pi bond. Here positive charge is adjacent to pi bond. So they are not equivalent. I cannot say they are equivalent. But their contribution is going to be less. So more or less this positive, negative, negative, positive overall will be cancelled out. Okay. Similarly, I can draw this structure as you are having something similar to this. This also will have something similar, which is this structure. CH2 double bond, CH bond, CH negative, CH2 positive. You have this structure. So both of them, this has positive, this has negative, this has negative, this has positive. So overall the charges will be cancelling out. Hence the resonance hybrid, I'm not showing any of the charges on the carbon. If you observe the resonance hybrid, even though the individual structures are having some some positive and negative charges, overall resonance hybrid is ending up with no charge on the carbon. Okay. So we are interested only in the pi bond distribution in here. Is this clear, everyone?
Yes, sir.
Okay.
Yes.
So if they are there, how many resonating structures should we count? All of them? How much ever unstable it is?
And no, you should not. You shouldn't be counting this. In fact, in this particular scenario, you need not consider this also. These structures are also not that significant. This contributes to 99%. Most of the uh, or else whatever electron density you have here, it is going to be much significant when compared to this. Okay. Or else I can say the bond order of this and this will be close to 2, but will be less than 2. The bond order of this will be close to 1, but it will be greater than 1. Okay. As the
Okay, sir.
this contribution is higher, I'm saying this will be close to 2, but will be like definitely less than 2 because there is some distribution happening. Everyone with me?
Sir, I have a doubt.
Yeah. Yes. Go ahead.
So, like in the fifth and seventh structures,
Fifth and seventh structures. Okay.
both of them have equal stability, right?
Both of them won't be having equal stability. In fact, seventh is more stable when compared to fifth. But the incremental change in stability is very less. They're almost same. Okay.
Understood. So
They're
that's why
almost.
there is no net charge on the hybrid, right?
Yes, exactly. That's why there is no net charge. But 7 is slightly more stable, it's very slight. But that doesn't make any difference, much difference.
Understood.
Okay. And you need not analyze in that minute details. It's not required. Okay. You can, depending upon the context of the question, you can answer. But here I'm saying that the reason for this having slightly greater stability is here you have a pi bond. Pi bond is nothing but electrons, right? So you
Yes.
have positive and electrons in vicinity, so there will be some attractive forces. Here pi bond is also electrons, negative charge is also electrons, so there will be some repulsive forces. Okay, so this becomes slightly better when compared to this. Okay, and next example for conjugated system, everyone. So this is one example of conjugate system. So whenever there is conjugate system, you can always have resonance, or you can always have overlap of several orbitals in order to make some electron cloud. Okay, some extended electron cloud where the electron densities in the electron cloud may or may not be same throughout. It depends upon the resonating structure contributions, or this is the actual structure that is observed for the molecule. Then in order to understand how this structure has happened, we are trying to frame a theory. Okay. By drawing possible resonating structures and by trying to assess the contribution of resonating structures, and thereby concluding, okay, this is the structure that is formed because of all of these structures. Everyone with me?
Yes.
Yeah. Next, allyl carbocation. Allyl carbocation, again, what you need to do, you need to analyze if this is a conjugated system or not. How to do that? Get the hybridization. What is the hybridization? sp2. When carbon has a pi bond, blindly it is sp2. Carbocation, carbon's outermost electrons are 4, removing an electron 3. All the 3 electrons are utilized in bonding, so there are no lone pairs, 3 side atoms, sp2. Agreed, everyone? So if this has a pz, this will be having pz. This will also have the pz orbital because this will be spx and py. So how you can show the orbital picture is carbon, carbon, carbon. You have an orbital here. You have an electron, you have an electron. This has a pz orbital that is vacant. Okay. You can show positive charge here, but you need not, in the orbital picture, you need not show anything. You can simply leave it as vacant. Vacant indicates it is positive charge. Okay. So now what to do? In order to form the resonating structure, you take this electron in here. Okay. Whenever you're taking the electron in there, you'll form a structure, carbon, carbon, carbon. You will have 2 electrons here. So you have 2 vacant orbitals now, which is nothing but this structure, right? You have negative charge here, positive, positive. But will we show this structure?
No.
No, because it is having high charges, you won't be showing it. How this structure got formed? Pi bond, take it here. You form this structure. You take the electron from here to here. Carbon, carbon. Now you have 1 electron here, 1 electron here. So you will be forming a pi bond. or else it's equivalent to negative and positive side by side, form a pi bond. So in reality, what you do, you can directly go from structure 1 to 3. Okay. You can directly frame something like whenever you are showing this, whenever you have negative and positive side by side, you just form the pi bond. Okay. Pranit, are you shooting any? It's like you are.
Sir, there's no current, sir.
Okay. You can tell your kids that you used to attend online lectures without current.
Oh, current just came.
And just came. Okay,
Radius of H.
fine. So whenever you are doing this, everyone, you can go from structure 1 to structure 3. You can directly jump. You need not show this. Okay. Negative and positive, whenever you see side by side, you simply form a pi bond. You form a positive charge here, you will get this. Fine. And in this case, this structure can be completely omitted, and the other two structures are equivalent structures, right? So I can form some resonance hybrid like this, plus 1 by 2, plus 1 by 2. So you have 1.5, 1.5 bond order. Agreed? Okay. So we answered the second question. When can resonance happen? Which is resonance can happen in conjugated systems. What are conjugated systems? Whenever you have symmetric p orbitals present on adjacent atoms. Whenever symmetric p orbitals are present on adjacent atoms, all the p orbitals are intermixing among themselves to form one uniform, not necessarily uniform, to form one cloud with a different electron densities at different places, which depends upon the contribution of resonating structures. Fine. So now what we will do is we will identify all possible resonating systems which are present so that we need not assess case to case. Whenever you are given any particular structure, we need not analyze if this is having symmetric p orbitals throughout or not. You will mark all possible cases where you will be having symmetric p orbitals. So once you see that case in the structure, you will say yes, resonance will happen there, and you will just directly start drawing the resonating structures. Fine. So the third question is, what are all possible systems where resonance can happen? Or all listing of all conjugated systems. First system which we already saw, this is read as pi alternate pi. Pi bond, alternate, pi bond. Alternate indicates you will be having a sigma bond. A pi bond alternate to a pi bond. So the example which we already saw, 1, 3 butadiene. The other example which we can list is benzene. Next example, benzene. I won't be showing orbital picture. I will be directly drawing the resonating structures. Can you see pi alternate pi alternate pi? This is completely continuous resonating system or conjugated system. You need to read this as pi alternate pi alternate pi alternate pi. So it is a closed conjugated system. Agreed? So in order to mark the resonating structures, what should I do? Break this pi bond onto this. Once you break it, what will you get? Everyone, what will you get? You have
Will be
negative
negative
charge
charge.
here and positive charge here. Remaining will be the same. Then what will you do? This negative charge
Will turn
will
into
form,
pi bond, and the next pi bond will form a negative.
it has to break because carbon cannot form 5 bonds, right? So here, then you will be having a pi bond here. The positive charge is placed here. You have negative charge here. You have a pi bond. In the next structure, this negative will be forming a bond. This will be going on to here. which will result in formation of, you will have negative here, you have pi bond here, pi bond, and you have positive. And in the final structure, you'll form pi bond. You have pi here, pi here, pi here. If you observe, whatever pi bonds you have, they got flipped, or else this pi bond has now came here, came here, this came here, right? Okay. So these two structures, in fact, these two structures will be the most contributing structures. Okay, because they don't have any charge. And these two structures are also termed as Kcule structures. Kcule. Okay. And the resonance hybrid is going to be due to these two structures. As these are having charges, their contribution is going to be almost insignificant. So if I take this and this, 1 plus 2 divided by 2, you will get the resonance hybrid, which looks like this, right? I have density here, density here, density here, density here, density here, density here. Hence, we show benzene as something like this. This with a circle. That circle indicates all the symmetric p orbitals overlapped among each other, or they formed one circular electron density.
Okay.
Okay. You can alternatively show it like this. Everyone, I'm not drawing anything. You can alternatively show it like this. You have sp2, 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 sp2. So you have pz, 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 pz. The p orbitals above the plane, this particular plane, combined among themselves. The p orbitals or p electron densities or these orbitals below the plane also combined among themselves. So you have one ring above and one ring below. Agreed? Because a p orbital or a pi electron density will be present above and below the internuclear axis, right? Okay. So you have these things combining among themselves, these things combining among themselves, and you are having one circular cloud here, one circular cloud here. Fine, everyone? Okay. This is the first conjugate system, pi alternate pi. Whenever you see pi alternate pi, there will be resonance. Next, pi alternate positive. Pi alternate positive. Example, allyl carbocation. You have again what you need to see. Again, we already we saw the standard allyl carbocation, right? Which is CH2 double bond CH bond CH2 positive. We already looked into symmetric p orbitals on this. So this is also the same sp2 sp2 sp2. So you have pz pz pz. So all of them will be combining among themselves, or else the positive charge will be distributed equally, right? Okay. So next system is pi alternate negative allyl carbanion. Yes, this is an interesting case, everyone. You have CH2 double bond CH bond CH2 negative. Okay. Tell me the hybridization of these carbon atoms. Everyone fast.
All of them will be sp2, sir.
Okay, this is sp2. And this one
The next is
sp2.
P2.
What about this?
It will also be sp2, sir.
Okay, but in reality, as per chemical bonding, we take it sp3, right? Carbon's outermost electrons are 4. Negative charge indicates you are giving an electron, which becomes 5. Out of those 5 electrons, only 3 side atoms are there, or 3 electrons are used for bonding. So 2 electrons are left. So 1 lone pair and 3 side atoms. Okay, this carbon is having 1 lone pair plus 3 bond pairs. So we may expect that to be sp3. We may expect that to be sp3, but in reality, what happens is it becomes sp2. Can anyone tell me why? Or
So because
Yes.
of resonance, there will be a partial double bond everywhere equally, so all will be sp2.
Okay.
So since
Because
electrons are migrating from p orbital to p orbital, there's only two orbitals involved.
okay. First of all, tell me why we used to place the lone pair or the negative charge in the hybrid orbital. What's the reason for that?
Because hybridization of orbitals brings stability.
Hybridization of orbitals brings stability and the angle will be greater. If you are making it sp3, everyone, if you are keeping it sp3, you will be having the negative charge or the lone pair with the other bond pairs at an angle of 109.5 degrees, or lone pair bond pair repulsions being greater, the angle will be greater. But that is the lone pair bond pair angle will be greater than 109.5 degrees, right? But if you are making it as sp2, what is the everyone? If you make it as sp2, the shape is trigonal planar, and you will be having the lone pair. You'll be having the lone pair at an angle of 90 degrees. Agreed? But if you are making it as sp3, you'll be having the same negative charge or lone pair at an angle of 1 naught or greater than 109.5 degrees. So 90 degrees is lesser when compared to this. Hence, we prefer to take the lone pair in the hybrid orbitals so that the angle between lone pair and bond pair increases. But here what we are doing is we are preferring to make it as sp2 and keep the lone pair in the pure orbital. A reason being, whenever you place the lone pair in pure orbital, then you can have resonance. Okay. What
Sir,
happens in resonance?
since for the p
Let me
orbitals you have
let me
charges.
let me complete. Let me complete. So this negative charge, whenever it goes in resonance, you can draw a structure which is CH2 negative, CH double bond CH2. And if you observe, both of these are equivalent structures. You can form the overall resonance hybrid as CH bond, CH partial bond, CH2. And this is negative by 2, negative by 2. So you're not having the entire electron density at an angle of 90 degrees, right? You are having only half the electron density at an angle of 90 degrees with the bond pair. Moreover, the negative charge also got distributed. So this is relatively more stable system when compared to having sp3 and negative charge at an angle of 109.5 degrees. So everything is with respect to stability. So as this is a more stable system, we are preferring to make this as sp2 hybridization and then distributing the charge so that the entire charge is not experiencing repulsive forces with that 90-degree angle. Everyone clear?
Yes.
Okay. So the final statement, conclusion statement is resonance participating negative charge or resonance participating lone pairs will always be kept in pure orbitals. Okay. Or resonance stabilized carbanions will be having sp2 hybridization. They won't be having sp3 hybridization. Is that clear? Okay. So you can mark it as a statement. Later on also we'll mark that. So you can, for now you can mark resonance stabilized carbanions are sp2 hybridized. Everyone please put your video on. I can see only Manideep. Everyone. Those who don't put their video on has no right to ask a question online. Okay. Next time I will completely ignore those who don't put their video on and ask a question.
Sir, can you give me 20 minutes? There's something going on.
Yes, yes.
Thank you, sir.
Fine.
So would you please also give me 20 minutes?
Huh? What?
So would you also give me 20 minutes?
Yes,
I have
yes. Something going on. Yes, yes. Fine. Okay, it's good to see many people turning on videos. Okay, fine. Next, everyone. So the first system is pi alternate pi. The second system is pi alternate the positive charge. Third system is pi alternate negative charge. Fourth system is pi alternate odd electron. Okay, or pi alternate free radical. So again, I'm taking example of CH2 allyl free radical, CH. I hope everyone of you know what is meant by allyl carbon, right? The carbon attached to double bonded carbon is called as the allyl carbon. This is the simplest allyl uh, substituent. Any modification of it will be called as allylic substituent, right? So this is allyl. Any modification of it is allylic substituent. Fine. So you have this free radical. If I show the orbital, I want to show the orbital diagram. If I show the orbital diagram, you have an electron here, you have an electron here, you have an electron here. So initially, the resonating structure is like, initially there is overlap between these two. In the resonating structure, what you can do is, you can break the overlap between these two and form the overlap between these two. Okay. You have something like this. Again, you have the same thing, but now you are showing the overlap between these two, which is nothing but this structure. C bond, double bond C, the free radical is here. Initially C bond, the free radical is here. Okay. We may not be able to show the hybrid of it, it's fine. Okay, you just say that there is resonance here. There is no representation for the free radical by 2, free radical by 2. It doesn't make any sense. You say that there is resonance happening in here. Fine. Okay, or all these electron densities are getting overlapped or getting intermixed. Next
So
system.
will both the compounds give equal contribution?
Yes, yes. They are equivalent, right? Once they are equivalent, they will give equal contribution. Fine, everyone?
Yes, sir.
Yes, sir.
Okay. Next, pi alternate lone pair. C double bond C. It can take a lone pair on it, and H2 lone pair. Again, if I mark the hybridizations, this is sp2, this is sp2. NH2 is expected to be sp3, but we will deliberately make it sp2 so that the lone pair will be present in parallel orbital. If it is present in parallel orbital, it can be distributed or it can be merged, right? So you can draw the resonating structure as the lone pair is converting into pi bond. The pi bond breaks on to carbon. C bond C. You have a negative charge here, double bond. As nitrogen is contributing both the electrons in the bond, it will be bearing a positive charge. If the initial structure is neutral, all of the resonating structures must also be neutral. Okay, so negative and positive, it's neutral, right? Okay. Similarly, you can give another example. C double bond C bond OH. You have two lone pairs. Out of those two lone pairs, now if you ask me the hybridization, even now the hybridization will be sp2. The other lone pair you keep that in hybrid orbital only. Okay, you don't keep that in pure orbital because only one lone pair can be distributed. At any instant, only one lone pair can be present in parallel orbital, right? It doesn't make any sense to keep the other lone pair in pure orbital because it will be less stable system. Agreed? So the hybridization of OH is sp2 but not sp. You make it sp2 only. If it is sp2, you can distribute that. You have C negative, you have carbon, double bond, OH, positive. The last system, lone pair and positive charge on adjacent atoms, which is a case of back bonding. It is similar to back bonding only. Suppose if you have this, you have lone pair and positive charge on adjacent atoms. You have this carbon as sp2, which is octet incomplete. This has a lone pair of electrons. It can donate that lone pair of electrons in coordinate bond to this so that it can become octet complete structure, right? Okay. So this is a case of resonance. Back bonding is also a case of resonance. So this also becomes sp2 so that the lone pair will be present in parallel orbital, or it can be donated into this vacant orbital, and you can show the structure as CH2 double bond OH positive. All right, everyone? Okay. And this has become octet complete structure from octet incomplete structure. Now the oxygen also has octet completion. We have a lone pair left on it. 1, 2 with hydrogen 3, 4, 5, 6, 7, 8. This also has octet complete because it is forming 4 bonds. So entire structure is octet complete structure. Agreed, everyone?
Yes.
Everyone? Sanjay, fine. You are listening, right? You are smiling. Hence, I'm asking. Yes, fine. So
No, sir, it was my
everyone,
brother, sir. He was making.
okay, okay. Everyone, so these are the this is the exhaustive list of all possible conjugated systems. Once again, the conjugate systems: pi alternate pi, pi alternate positive, pi alternate negative, pi alternate free radical. Then you have pi alternate lone pair, then lone pair and positive charge on adjacent atoms. Lone pair and positive charge on adjacent atoms. I'm not marking any positive and negative charge on adjacent atoms because obviously you will be forming pi bond between positive and negative charge. Okay. So it's not like a resonating system.
So in the sixth question, the second compound is highly unstable also.
Which one? Which one?
The sixth question, second compound is highly unstable.
You're saying this is highly unstable.
Yes, sir.
Okay. How many of you feel the same? Raise your hands. This is highly unstable. Shriram, why do you feel this is highly unstable?
So because oxygen is highly electronegative in comparison to the other atoms present in the given compound.
Okay.
So if there's a positive charge on oxygen, which means that oxygen being highly electronegative is highly unstable because it has the increased tendency to be negative, but it's positive in nature.
Okay. So if let us say Ambani is there, he is richest, but he is doing some donation. So that makes him highly unstable.
Oh,
No, right? That donation makes the poor happy. So this is like this carbon is poor because it is octet incomplete. Okay. By giving the electrons in coordinate bond, both the electrons will be part of this as well as this. Overall, oxygen may have that positive charge, but the entire compound or entire structure is octet complete structure. So this is highly stable when compared to this. It's not highly unstable, it is highly stable when compared to this because it is an octet complete structure. Though oxygen is bearing a positive charge, it is going to be highly stable as it is completing the octet of this. Everyone with me? Okay, we will explore such things soon, but as of now, this is a resonating system. Everyone, 6 resonating systems. Everyone clear? So if that is clear for you, quickly draw the resonating structures of these two. Whenever you are showing the resonating structures, you always migrate the electrons from higher density to lower density. Okay,
can we use
you can
that
always, you
figure?
can, huh?
Can we use
What?
the line representation for solving?
Your wish, whatever you feel comfortable. It's fine.
Get food and all and comes. Fine. Do para.
Just show the resonating structures. You can draw other resonating structures which are quite unstable as well, but you need not show them. Just show some possible good resonating structures.
Sir, I have a small doubt.
Yes.
So the resisting structure with a double bond will be more stable than an alternate positive and negative bond, right?
Yes. Hence, we are not framing for forming it. Yes.
Okay.
Never form more charges. Everyone, never form more charges. If you have one charge, try to form resonating structures which has only one charge. Okay. You draw. You draw. I will also show you.
It's first story. Rod.
Okay, I hope it's done. Everyone, what to do? You take this pi bond and convert this into negative charge. Parallelly, you form a bond between these two. Negative and positive are side by side, right? Form a bond. So you'll have something like this. CH2, double bond, CH, bond, CH. I have a positive charge here. I have CH, double bond, CH2. Then you can make this onto this. You have CH2, positive, CH, double bond, CH, bond, CH, double bond, CH2. So if you identify the conjugating system here, it is in a way pi, alternate positive. You have this entire thing as a conjugating system, right? In here, you always shift the electrons from higher density to lower density. So take this negative to pi bond. Carbon cannot make pi bond, so break it onto this. These are the simplest things. You have CH negative here. Then you have CH double bond CH2. Then you can have this negative charge coming onto this. You have CH2 negative, CH double bond CH bond CH double bond CH2, right? And then fine. Okay, solve this question. In which of the following compounds or species the positive charge or the lone pair is in resonance or is in conjugation with the pi bond? Resonance is nothing but conjugation. the positive charge or the lone pair must be in resonance or in conjugation. What do I mean by that? The positive charge or the lone pair is able to distribute itself. We will take this question, we will solve this, and we will take a leave. I'm leaving you fast because my battery is about to die.
So class till 9 o'clock you told us.
Yes, I may not have my battery till then. My battery in the sense, a mobile's battery. Tomorrow we will have 7 to 9. I will keep it charged.
Sir, I think I got the answer.
You got the answer for everything?
I, I got that all of them can show conjugation.
You're saying all of them can show conjugation. Okay, that's one of the answers. Everyone.
So what do you mean by one of the answers? Like
So
are multiple things correct, or is it one of the following pictures?
if it is that simple, I won't be asking the question.
Sir, all the structures show conjugation, sir.
All the structures may show conjugation, but I am interested in can you distribute the positive charge in all the structures, or can you distribute the lone pair in all the structures in resonance?
Oh, sir. I'm getting 2 to 5. Sorry, not the first one.
Not the first one. Okay. 2 to 5 structures are structures where you can have participation of lone pair or the positive charge in resonance. Everyone, 2 to 5 is one of the answer.
Yes, sir.
Yes. And any other answers? I'll wait for a few minutes. It's fine. I have 20% charging. Everyone, please put your video on.
Maybe not the third one.
Sorry.
Not third one.
Not the third one. Okay. So as of now, not the third one. Remaining all 4.
1 minute, sir.
Okay.
Sir,
Yes.
when you do the structures, you do it step by step. Like first it goes to the bond, and then it goes to the next atom, sir. Can it
Yes.
directly go to the next atom without forming the intermediate bond?
You can show that. See, all these structures are hypothetical only. It's not like it's going or anything. The structure exists as some hybrid, which is the distributed electron density. So we are trying to explain those things, right? So whenever you are trying to form the structures, all the structures, it's better to show one after the other so that you won't be missing out on any of the stable resonating structures. If it is unstable, you can directly go to the other structure.
Sir, from let's say C1 to C2, sir, I can't form a bond between C1 and C2.
Which example are you talking?
Not
referring to?
sir, specifically means the third example, sir.
This one. This one.
Yes, sir.
Okay.
I can't have N and C bond formation, sir.
Okay.
But can I just directly take that bond pair and transfer it to the N, like without
Yeah,
forming
yeah,
the intermediate bond?
yeah.
Sir,
If you feel like doing it, you can do it. You can do it.
sir, I'm getting
Then
1 and
how
3
this?
cannot show resonance.
Yeah, 1 and 3 may not show resonance. You are saying
Yes, sir. 2, 4, and 5 I'm getting.
2, 4, and 5. You are getting okay. Okay, everyone. I think enough time. Shall we discuss?
Okay, sir.
If you want more time, I will give you. Please let me know. Everyone. Very important example, everyone, very important example. So please be focused. Okay. See, I will address the first question towards the end, one towards the end. In case of two, see, if you are saying that it can participate in resonance, you should be able to draw the resonating structures. This is the first thing. Okay. So make the hybridization of this nitrogen as sp2 so that this can be in conjugation. Carbon cannot make 5 bonds. Yes, you can draw a valid resonating structure. Double bond NH2 positive. You give negative charge here. You can draw other resonating structures. So this will go here. I'm trying to draw all possible resonating structures. Whenever you're doing that, at the end you should be forming back the original structure. That indicates you have shown all possible resonating structures in the process. And H2 positive. In the next structure, this will go here. This pi bond will come onto this. Everyone with me? Are these all valid? I hope I'm not making any mistake.
Yes, sir.
And H2 positive. So finally, this will form a pi bond. The pi bond will convert into lone pair. Agreed? Yes. In the second question, yes, the lone pair is able to participate in resonance or is in conjugation with rest of the parallel p orbitals. Or these things are going to intermix among themselves. Fine. In the third case, if you draw the resonating structure, if you feel like, okay, pi alternate positive, you have formed the structure by making the pi bond. You are forming 5 bonds with the nitrogen.
So octet will be valid.
The structure itself cannot form. Nitrogen cannot expand its octet. Moreover, you get the hybridization of this nitrogen. What's the hybridization of this nitrogen? It is sp3, right? It has 4 sigma bonds. It is sp3. There is no symmetric p orbital that is left so as to intermix with these p orbitals. Right? There is no pure p orbital that is left on this, which can intermix with this and you can have resonance. So this positive charge can never be distributed. Okay. So whenever you see pi alternate positive, don't blindly say it is a resonating system. Okay, you should be careful. You should be careful. That's what I'm trying to say. That's it. Okay. So you should be able to draw valid resonating structures. This is not a valid resonating structure because nitrogen can never form 5 bonds. Either you can do that or you can do the analysis, the original analysis, which is of symmetric p orbitals. This doesn't have any symmetric p orbital with the adjacent carbon. Fine. Okay, next this part. Okay, pi alternate positive. Yes, it's a very good resonating system. You can draw all the resonating structures possible. Fine. I hope there is no doubt in this. Okay, what I want every one of you to attempt is this is lone pair alternate lone pair. Yes, you can make this as sp2. You can have a parallel p orbital. You can take these things in resonance or all of these p orbitals can intermix. I want you to draw all resonating structures so that towards the end you should form back the original structure. Drawing resonating structures also you should be familiar or you should be well versed with it. Draw all resonating structures of this and tell me number of resonating structures which you are forming. Yes, you can make 2 charges. Fine. Don't make too many charges. You should be forming at least 2 charges. Tell me total resonating structures you have formed. You do solve. Answer, please.
So I got 4 structures in which the nitrogen atom has a positive charge.
4 structures in which the nitrogen atom has a positive charge. Okay.
So am I correct in assuming that this and the regular structures are the main contributors?
Once again.
I found 4 structures in which nitrogen.
Yeah. Has positive charge, you are saying that as the major contributors or
That and
significant
the
contributors.
main one, sir.
Main
That
one.
and
Okay, so total 5 you are saying.
yes, sir.
Total 5. Okay. I need to once check. I need to myself draw and check.
Under any with under any other with major contributions,
No,
these are the main ones.
these will be the main ones. Nitrogen bearing a positive charge will be the main ones.
Okay.
That with this. The contribution of the original structure will be higher because it has no charges. Everyone, shall we draw the resonating structures? Or else I already drew them. Once let us see them, look at them. Everyone, the lone pair is forming a pi bond. The pi bond will break onto this to form a negative charge. Then you have negative alternate lone pair. So negative charge will be forming a pi bond. Carbon cannot form 5 bonds, hence breaking this onto this as a negative charge. Then remember or understand this negative and positive charge are not the resonating system. Is not the resonating system. If you feel that way, if you form a pi bond, that nitrogen will be making 5 bonds, right? Which is an invalid structure. So this negative alternate pi is the system, but not negative and positive. Understood, everyone? Okay, this negative and pi are the systems. Okay, so if you have negative charge here, you have 2 electrons here. If you have a pi bond here, you have electron, electron. So these things, these are the things which are in conjugation. Okay, so negative alternate pi is the system. So whenever this negative charge forms a bond, nitrogen, as it cannot form 5 bonds, this should break onto this to form negative. Then negative alternate pi bond is again the system. So this forms a pi bond. This converts into negative charge. Negative alternate pi bond is again the system, forms a pi bond, and this pi bond will now convert into lone pair. So you got back the original structure. So the total things are these 4 as well as this. So total are 5. Yes, Mandeep, you are right. Okay. Everyone observe, you need to eventually get back the original structure. You should not form any pi bond here and think, okay, this is also that will also be a resonating structure. No, it won't be, because it will be an altogether invalid structure. Okay, you should take care of those minute things. Everyone with me?
Sir,
Yes.
why are the third and fourth one different, sir?
Why are the third this and this? You're saying
No, I mean that and left.
that and left. These two are different because this carbon and this carbon are different, right? They are equivalent. I can say they are equivalent, but they are two different structures.
But I can flip it in the plane, right, sir?
Yes, but still this carbon is different. No, this carbon bears the negative charge here. This different carbon is bearing the negative charge. It's load distribution, different load distribution. No,
Okay, sir. Okay.
altogether these two are two different individuals. Okay. Once the negative charge is borne by this, and like other the negative charge is taken care by this. So you are distributing it. You are actually distributing the negative charge on two different carbon atoms.
Okay, sir.
Or in all the resonating structures you see, the negative charge is getting distributed on all of the carbon atoms. This has it, this has it, this has it, this has it. If you omit this structure, then you won't be, if you add only these structures and take the average, this carbon won't be seeing any negative charge, right?
Okay, sir. Okay, sir. Understood.
Okay. So this is also a structure. It's not about, yes, they are equivalent, but they are not same. Okay.
Okay, sir. Thank you.
And so you, as you just came from isomerism, you tend to flip these things, rotate these things. So don't do such things. They are two different structures. Okay. Okay. Next, in this case, In this case, if you are drawing a resonating structure, everyone, if you try to form a pi bond and if you do this, this nitrogen will become sp hybridized. Okay. Or it cannot happen. Why it can't happen is the resonating system is pi alternate pi. This is the resonating system. Let me explain how. The lone pair is not in resonance. Very, very important. Once you understand that, other things become obvious. Everyone, very important. Concentrate. Most of the questions are directly based on the application of this. See, you are forming a pi bond, or first let's get the hybridizations of these things. Or let's form the pi bond. Okay, you have a pi bond between the carbon and the adjacent nitrogen, right? You have a pi bond between these two carbons. You also have a pi bond between these two carbons. Agreed? So you have one electron here, one electron here, one electron here. Because a pi bond is always formed between symmetric orbitals. So if you already have an electron occupying a pure p orbital, which is involved in the pi bond formation, where will you place the lone pair? You cannot have another orbital parallel to this, which is having a lone pair, right? There cannot be two px orbitals, right? Or there cannot be two pz orbitals, right? One is having one electron and the other is having two electrons. Can you have anything like that? Agreed. So you cannot have the lone pair appearing here because you already have a pz orbital that is involved in pi bond formation with the adjacent carbon. So whatever p electron or whatever lone pair is there, that should be placed in the hybrid orbital. I will place the thing in hybrid orbital because if you try to place it in pure orbital, this hybridization has to become sp and sp becomes linear. And if you have a pure orbital, the angle will be 90 degrees with it. Let us say nitrogen, you make it sp. So in that case, if you place it in pure orbital, you'll be having an angle of 90 degrees. What's the purpose of keeping the lone pair at angle of 90 degrees and have more repulsions? Right? You take this as sp2 so that you will have the lone pair at an angle of 120 degrees with the bond pair. Agreed? Okay, so the lone pair is present in a perpendicular orbital but not in the parallel orbital. So you have the resonating system as these things overlap. So all these things are going to combine among themselves to have that resonance. So you have the orbitals which are placed above as well as which are placed below, combining among themselves to form a ring above and ring below, just like benzene. Okay, the only difference is you have a nitrogen here. And the lone pair is present in a perpendicular orbital. So it can never jump here to participate in resonance, or this orbital won't be intermixing with this. It can't happen. Agreed? So whenever you see, blindly you can say, whenever you see double bonded nitrogen and a lone pair on it, that particular lone pair can never participate in resonance. That's the final concluding statement. So if I give you a question like this, okay, if I give you a question like this, I am asking which of the following lone pairs are in resonance. What will be the answer? A can be in resonance.
Question.
The question is, you have two lone pairs, a lone pair on this, lone pair on this. I'm asking which lone pair is in conjugation, or which lone pair can be distributed, or which lone pair is in resonance.
A can show.
A can show in A can go in resonance because this lone pair is like similar to pyrrole kind of compound, right? This is pyrrole. Okay, this is pyrrole. So lone pair alternate pi bond, and this is pyridine. Everyone, this compound is pyridine. So pyridine type of nitrogen's lone pair will never participate in resonance. So this is double bonded nitrogen's lone pair. It cannot participate in resonance. So in the second question, which of the following lone pairs can participate in resonance? Fast.
A can only participate. B cannot
A
participate.
can participate, B cannot, C cannot,
Not
D can,
B
E cannot.
cannot.
D can write because it is lone pair arginate 5 bond. Understood? As simple as that. The understanding of this is important to understand the comparison of basic strength later on. Okay. All these are interconnected, everyone. So understand which lone pair can participate in resonance, which cannot participate in resonance, understand which can go in conjugation, and understand what is meant by conjugation first of all. What is meant by resonance hybrid, how we are arriving at resonance hybrid, etc. etc. Fine, everyone?
Yes, sir.
Okay. We will see this question and we will wrap it. Which has a greater C bond Cl bond length? Which has a greater C bond Cl bond length among 1 and 2?
Is it the first one?
There is
One, sir.
the second one.
Second or first? C bond Cl bond length.
First one, sir.
First one, sir.
First one.
First one, because in second you have some resonance. Because of resonance, you will be having a resonating structure which has a double bond between carbon and chlorine, right? Yes, the resonating structure's contribution may be different, but it is still having some contribution which will lead to some partial double bond character. Here there won't be any resonance, so it is only single bond. A single bond will always be longer bond when compared to a double bond, right? Agreed, everyone?
Despite the size of the chlorine's atom, its resonance brings it much closer.
Chlorine atom is both the cases, it's chlorine atom only, no?
Yes, sir.
Right?
Okay. Understood, sir.
Okay. Okay, everyone?
Yes, sir.
Okay,
Yes.
I'm ending here. We will be able to complete the syllabus peacefully only, I guess. Okay, tomorrow we have 3.
So the question which you initially gave, which will show resonance, the answer is 2, 4 finally, sir.
Yes, whatever you told, that's the answer. 2, 4, 5. 1 and 3 cannot participate. Everyone. Final conclusion is that right? This cannot participate. This cannot participate. This can. This can. This can. Okay, we will be able to complete the syllabus. Tomorrow we have 3 hours and we will again take 1.5 to 2 hours tomorrow as online. And after tomorrow, I will ask maths sir if at all it's possible. So we will be able to finish. But practice wise, whatever you are doing in the class, yes. Maybe a Friday I will post the previous VAT paper. You can solve it. We can discuss on Saturday. Fine.
Okay, sir.
Yeah.
Okay,
Thank you.
sir.
Thank you, everyone. Thank you.
Thank you, sir.
Can I ask some doubts if you don't mind?
Thank you, sir.
Yes, you may.